Right, design of a gravity recovery gold circuit, or as it's called, a GRG circuit. Where do we start with this kind of design? So just like in real estate, test work, and test work. That's the most important factors for the successful design of any project and any success of that project. André Leplante developed a well-proven standard test quite a while ago, which is still used throughout the industry today. This test has evolved a little bit and is now called the EGRG test, or the extended gravity test. What you get from this test is your ore content, your size by liberation, and also all this information is required for if you want to continue further on with modeling or simulation in your project. We'll discuss this a little bit more in detail later. Now, new feed is still the best sample to use for decision making. But when you do set up your test work campaigns, please use samples that does not contain any lockup, circulating loads, or a stream that cannot be upgraded. For example, a non-GRG stream. Things you need to consider for when you want to install a gravity circuit. The first thing is an economic evaluation. Now, this is quite important to decide if your project is actually feasible or not. There's a very rough rule of thumb in the industry which says 25%, if you have less than 25% of GRG and it's in the fine fraction, then your project is not feasible. But don't go with that. Do this economic evaluation. Then we get to the big question. How much extra gold do you recover? Is it really early revenue? This is quite a very big debate in the industry, but I think the industry have settled now that if we do install a gravity circuit, we can expect about a 1 to 3% additional recovery. But it's not really a recovery so much as what it is everything that's in the rest of this presentation. Now, André also published in one of his papers that you can expect about a 0.5% increase for every 10% that you treat of a flotation circuit, and a 0.2% increase for any 10% that you treat in a cyanide circuit. So we do have some literature backup, at least for this. Now, gravity circuits remove quite a large portion of gold and almost all of this big gold, or the nuggets like we like to call it. So there's definitely savings downstream. And these are normally when we have lower carbon strippings, in other words, lower elutions or less elutions. And also the gold loading on the carbon becomes drastically less. The whole inventory becomes less. But what is nice thing, all this fine gold that we always lose from the circuit now also carries a much lower content. So the gold losses from the CIL or CIP circuits become less. On occasion also, there has been some places where they were able to lower their cyanide concentrations in the CILs or the CIPs. But I think we can all agree that when you remove a big piece of gold from the circuit, you will have downstream benefits and especially OPEX benefits. Now, the big thing is theft and security. Personally, I believe that this is where we have the most increase in recovery. As you know, gold just tends to accumulate in every sump, pump box, pipe, or any place where it can trap. So by removing this early on in the process with a gravity circuit, you actually remove a lot of this temptation or even opportunity for theft to take place, and you start recovering stuff that has previously been lost by theft. Then there is an abundance of this coarse gold circulating in the circuit. So the whole gravity or the whole milling circuit actually loads up and becomes very high in grade. And we have a lot of lockup between liners, for example. So what is this EGRG test? Okay. Firstly, before you go down this route, you need to know your ore body. So a scouting test is required up front so that you can do a proper setup for test work campaigns. Now, this EGRG test is a 3-stage sequential liberation and recovery test. That's quite a mouthful. But the test basically assesses the amount of GRG in the sample by feeding it through a batch centrifugal concentrator at different grind sizes to maximize the chance of gold liberation and recovery. This progressive grinding approach then limits the smearing of the gold and allows for the recovery of the gravity gold to happen as it becomes liberated. So it sounds like quite a heavy test, but if you look at the schematic, you can see it's actually a very simple and easy test to perform. Like I mentioned previously, this now is a set of results that you'll get from it. And it's very important that you have this full suite of results for future modeling and simulation work. 2 things definitely spring to mind. Firstly is your GRG content. That's what you are trying to get from this. But also now, if you look at that calculated feed grade and you compare that to your actual grade that you started the test of, you can actually see your nugget effect, and you can start giving a good feel for what you can expect in your process. You can actually take this results and also plot it on a nice graph, and then even put your circuit grind against that, so you can get a good feel for what would happen in your circuit once it's installed. Now, all of us know that we can never duplicate test work in a production plant. It is just never going to happen. So you need to derate your test work to make a decision. Now, Andre, for example, mentions that in an extremely efficient circuit, which we all know never happens in a production plant, you can expect 2/3 recovery. But it's not uncommon for most people at this stage to discount by 50% to make their initial decision to proceed with GRG or not. Then the next stage is this modeling. There is various vendors and companies out there that's able to do quite detailed EGRG modeling work. What you do is you give them your EGRG test work results, your planned circuit configuration, the equipment you're going to install, and they do a beautiful model for you. But I seriously recommend that when you do this, still do all 3 the configurations. In other words, cyclone feed, cyclone underflow, and mill discharge, no matter what you're planning for your project, because that gives you a sound basis for your decision for that circuit, and even will show you any faults or problems that might be in your design. There's also the Mira P420 project available. This is supported by various companies out there and have a very strong technical backup that can assist you with modeling work, the explanation of the models, and even some suggestions of what else to do to get better results. What you'll need for inputs is obviously your EGRG test. And at this stage, you should have made a decision of how much of the circulating load you're planning to treat with your plant. In this model, there's also cyclone efficiency, which we'll definitely discuss later, the concentrator efficiencies, circuit efficiencies, gold room efficiencies, and also the breakage rate between non-GRG and GRG. So all of this is built into these models, and they will use this then to predict the outcome for you. So from it, you will get a very nice graph with a percentage of circulating load versus recovery. And at the same time, they'll even give you very nice tables for this. It's very important to just sit and look at this and see that on average, most of the GRG plants installed in the world only treat between 10 and 40% of the circulating load. And that's because of that law of diminishing returns. You can see there that as soon as you go over 40%, the graph starts to plateau off. And the additional cost for installing more equipment doesn't really warrant the payback that you'll get from it. So that's why most of the plants cut off at that. Unless they have very, very high GRGs, then sometimes they will go up to 50 or 60%. The second output that you'll get from it is what they call the Mira classification scale. And this immediately gives you a good representation of where your ore body is sitting with regard to other operations and the results from the EGRG test. And you really want to be on the right-hand side of moderate. This is much easier plants to install with very good payback periods. The more you go left to the finer and the ultra finer, it's more difficult circuits, and that payback just becomes longer and longer. This model does have another benefit, though, that even if you have an existing plant installed, you can do this test work and give them this information for modeling. It will give you a very good idea of where you have pitfalls in your circuit and what to do to actually get your circuit to operate more efficiently. Right, now you have your simulation work and we kick into the design. First thing we go back to again is that proper economic evaluation. Gravity recovery is not as economically significant as what grinding, flotation, and cyanidation processes are. That must be your key focus in your design. The gravity circuit is really only an add-on to a plant for extra benefit. So you have to spend that time on the rest of your plant. If you're going to do a greenfields or a brownfields installation, will make quite a big impact on this decision. And then, of course, again, we get back to the additional recovery and the downstream benefits, which will probably make up your final decision if you want to proceed with this project or not. It's not uncommon also for a lot of projects to actually defer the gravity installation to a later stage and rather do it as a retrofit or a brownfields expansion once they've actually accumulated quite a bit of working capital. But with gravity circuits, like probably most designs, there's not a one-size-fits-all. You have to do this economic evaluation and then make the decision and proceed from there. Now, as the designer, normally you would not have been part of this upfront decision-making and test work campaign structure. So you need to know what samples was used during these campaigns and what campaigns were actually run. Normally, to install or run a very lengthy, costly test work campaign for gravity is never a good idea, because all we need is really a small representative sample, enough to do GRG work to make that decision, which is fine. That's what makes it so appealing. But you need to know that to build that into your design. And then also target all the gold particles in that classification range and not just the exceptionally coarse particles. Then we get again back to that derating and descaling. So you need to derate your test work like we've just discussed, but you also have scale-up factors that you need to apply to your design. There's various benchmark figures out there, but if you do have a conservative economic evaluation, that definitely does help you in the design. Now, this is probably one of the key things that you need to consider when you do your design. The breakage rate of gold is always lower than ores, and we get a much higher circulating load of gold with higher gravity gold numbers. The following are some points which give you some guideline, and it's quite well published, where they talk about gold grinds between 5 and 20 times slower than its gangue. Almost all of the gravity gold fed to a cyclone reports to the underflow, unless you have a two-stage classification circuit installed. Luckily, we don't have much of those anymore. 75 to 95% of minus 25 micron GRG still reports to cyclone underflow. And that's one that really needs to be considered. Gold particles greater than 75 micron can circulate up to 50 to 100 times in the grinding circuit, unless there is a gravity circuit installed. And then once a gravity particle breaks, 90% of its fragments are now gravity recoverable. What does all this mean? It means you need to understand that gravity behaves completely different in a milling circuit, and you need to account for that to make sure that you have maximum opportunity to recover this gold from the circuit. Then plants, they have excellent upgrade ratios. We get 1,000 to 1 upgrade ratios, very high concentrates, but they have very low and quite poor stage efficiencies. We only get about 20 to 40% from a single pass on recovery. So they rely heavily on the effectiveness of the cyclones to keep the gravity gold in circulation for them to have multiple opportunities to recover this gravity gold, which gets us to that cyclone efficiency that I've mentioned previously. When you do your modeling work, you'll see that cyclone efficiency has got a big effect on the actual outcome from these simulations. Now, in the olden days, we had pre-leach thickness, but all new plants now don't have pre-leach thickness. We run cyclones at much higher feed densities, which means they have lower efficiencies, which means we have more losses. We are piggybacking onto the grinding circuit, and ultimately the grinding circuit is the heart of the plant. So in actual fact, there's not much we can do but to live with whatever the circuit requires regarding density and therefore efficiencies. So all you can do is design your circuit to give these concentrators maximum opportunity to grab this gravity gold from the circuit. Then as a designer, you might be faced with a point where you have to say, no, this is not the answer for this project, and walk away from it. If gravity gold does not add value, do not install it for just the sake of installing it. There's other technologies that's much better suited. For example, if you have a lot of fine gold, then rather install a flash flotation circuit. So do not just install for the sake of installation. Now, gravity circuit operation can be very, very challenging because of the material that we're trying to use. It's not the simplest of material to pump around and move around. So you need to design a circuit that is easy to operate, easy to start and stop, and does not affect the downstream, and definitely does not affect the milling circuit. The milling circuit must be able to perform its peak performance at all times. We then also now have a beautiful concentrate that we've spent so much money and time to get, so we need a proper downstream recovery system. A lot of people skimp a little bit on this because it is quite high in capital and also not the easiest of circuits to install, but spend the time and effort and money to design a proper downstream. Personally, I still believe that leach reactors and electrowinning is the better suited option with gravity concentrators. Then the water balance. You would fall on your back when you see the amount of water these concentrators add to the grinding circuit, and actually the whole circuit by itself. You have to do a proper and a detailed water balance to make sure you do not affect your milling circuit and the downstream with all this additional water that you're adding. If you're installing a lot of concentrators, you will be required to install additional equipment to do any density corrections. And then security. You now have a concentrate sitting at over 1,000 grams per ton of gold. And no matter where you are in the world, that is security risk. So you have to decide in that area what is required, and then design and install correct security measures to protect that very hard-earned concentrate and getting it through to the gold room safely and without losing it, and therefore losing your recoveries. There's a lot of other design considerations that you have to take, but this is the ones that I think is more applicable specifically for gravity. Then we get to the practical considerations, and oh my word, now we're in a bone of contention. There is so much different views in the industry of where to install this. Do we install it on cyclone feed, cyclone underflow, or mill discharge? Now, cyclone underflow tends to run at very high grades because of the circulating load. So all the older installations always immediately went for the installation on cyclone underflow. However, research has shown recently that cyclone feed and definitely mold discharge is better options for installation. The higher grades of the cyclone underflow might be an advantage, but it's sometimes outweighed by the difficulty of treating this high density of the cyclone underflow. If we just look at the cyclone underflow to cyclone feed grade ratio, the moment you install just one concentrator, your whole circulating load starts dropping and it will reach a new equilibrium. And the more you install, the more this equilibrium moves closer to the actual grade of the cyclone feed, which then totally negates the reasoning for putting it on cyclone underflow. The screening efficiency on cyclone feed is also far better than on cyclone underflow, because with the cyclone underflow, we need to install a lot of water to get efficiencies up where we don't need that for the cyclone feeds. Then also, recent studies have shown that the concentrators actually perform much better at about 45% solids compared to the 60 or the 65s that we run when we're in the cyclone underflow configuration. Most of the installations have always installed a 2mm screen and 60 Gs concentrators, but I urge you to go back to your test work. See where your gold lies and where your liberation sizes are, and then make it the correct decision for your project and install a size and G-force machines to suit that specific ore body or your existing plant in operation. Feed to the concentrators are definitely an area where you need to spend a lot of time. These are batch units, so they run between 30 minutes to 2-hour cycles and then go to a 3 or 4 minute flush cycle. You need to take these concentrators offline quickly, let them do their flush cycles, and then bring them back online very quickly without starting and stopping additional equipment or upsetting the rest of the circuit. So again, design something that is easy to implement, quickly to switch, and do not choke up or actually cause a potential lockup for gold. Now, where and when and how big to install is probably a 2-day seminar by itself. Again, just go back to say it's got to be easy, it's got to be compact, and use gravity as much as possible. And if you can install it right at the back of the mills, it's always beneficial. But if you're doing a brownfields expansion, it's not always that available to you. But you have to look at what you have available, what your project requirements are, and then try and do it as easily as possible. There's also very good papers available with checklists for you to work through to make sure that you cover all the little things that might catch you out during the actual detailed design of a project. Then lastly, the main thing here for the success of an operation is fluidization water. If you do not have proper and very good quality fluidization water for these concentrators, these plants will never perform well. So know what water is available to you, and if you have to, design water treatment plants in to give you good quality water. Most of the vendors have specs available, which is roughly about less than 1,000 ppm and less than 20 micron TSS. But speak to the vendors and make sure you know what's the requirement. I also urge you to put in dedicated fluidization water pumping facilities, and do not rely on the rest of the plant to give the water quality as well as quantity for these units to operate. So that's GRG in a nutshell. Obviously, it's a much better topic or bigger topic, and much more to learn from it. But assess each project as it goes, and then hopefully this was helpful in some way or another.